So an experiment is a process to test a hypothesis, and a hypothesis is a statement you want to test. An event is a well-defined set of possible outcomes of the experiment, and sample space is all possible outcomes of an experiment. So to help us understand these terms, we're going to go through an example. So in our example, our hypothesis is, if I roll a die 4 times, we are more likely to roll a 6 50% of the time. So basically my hypothesis is what I'm predicting will happen. That's something that I want to test. So in order to test this hypothesis, I have to conduct an experiment. And how would I conduct the experiment? I would conduct the experiment by rolling the die 4 times. And then I would record what my outcomes are each of those times. So for example, let's just say I roll the die once and I get a 2. So let me write this out so it helps. So let's just say that trial 1, I roll a 2. And let's just say I roll it again, because we're doing it 4 times. So trial 2, but let's just say this time I get a 3. Trial 3. Let's say for trial 3, I roll a 6. And let's just say that for trial 4, I roll a 1. So these are the trials of my experiment. And looking at my results, which is 2, 3, 6, and 1, did I get 6 50% of the time? The answer is no. I only got 6 25% of the time. So that means my hypothesis isn't true, and we don't have evidence to support it. The next thing we're going to look at is sample space. And sample space is denoted by capital S. And it's going to include all the possible outcomes for our experiment. So before even rolling the die, I know that the possibilities I can get from rolling the die are 1, 2, 3, 4, 5, 6. And the reason why I know that is because on a die, there's 6 sides, and on each of those sides is the corresponding number of dots. So like one side's going to have 1 dot, another side 2 dots, 3 dots, 4 dots, 5 dots, and 6 dots. So those are the possibilities that I can get. Can I get 7 dots? No, because on traditional die, there's the maximum number of dots that you can get is 6. Okay. And then we're going to look at events. So events are possible outcomes of the experiment. So if we look at here, it says A equals 2, 3. We denote events with a capital letter, and then we put the outcomes in curly brackets like this. Okay? So one event could be we get 2 and 3. Or another event, B, could be we get 1, 4, or 6. Or another event could be C equals 1, 2, 5, 6, which means we rolled a 1, rolled a 2, rolled a 5, and then rolled a 6. Elements are each possible outcome in a sample space. So if we look at our sample space S, 1, that's one element. 2, that's another element. 3, it's another element. 4 is another element. 5 is another element. 6 is another element. So in this sample space S, we have a total of 6 elements. Okay. Containment is represented by this symbol right here, which is like a long C. And here we have A, and then that symbol, and B. This translates to A is a subset of B. This can also be stated as B contains A. Next, we're looking at null sets. So a null set is denoted by curly brackets, and then we put a little 0 with a line through it. Basically, null set, you can just put 0 with the line. You don't need the brackets, but it's kind of nice to put them. And whenever you see the word null, just think none or 0. So for example, babies' birth weights include 0 pounds. Our set would be the curly brackets and a 0 with a line, because This is impossible. It's impossible for a baby to be 0 pounds. Okay, so now we're going to do more practice with sample spaces. So if we flip a coin, the possibilities are heads and tails. So that's why I wrote S equals curly brackets HT. The order that you write the possibilities, it doesn't matter. So I could have just written S equals TH. Or let's just say that I wanted to write words instead. That's totally fine. You can just write S equals heads, tails. Or you can write S equals tails, heads. Every single one of those possibilities that I just gave you for the sample space is okay. And for your answer, you would only have to write one, unless your teacher asks you to write it in multiple different ways, but I don't think so. Most times they're just going to be like, what's the sample space? So you just pick one of these options and then write them down. Okay. So it says flip a coin twice and record each outcome. Okay, so for the first one, we look at our sample space. We have HH, TT, HT, or TH. Okay, so remember what I said. I said the order that you write each of these elements, it doesn't matter. So I could have done S equals HT, TH, TT, or HH. Or I could totally switch that up. It doesn't matter, as long as I just put in what the possibilities are. Okay, this next example, it says, flip a coin twice and record the number of heads that show. Okay, so here for my sample space, I got 0, 1, and 2. And now I'm going to show you how I got 0, 1, and 2. Okay, so let's just say trial 1. You get 1 head, 1 tail. So the number of heads that you got was 1, so you're going to get 1 head. Okay, let's just say now you did trial 2. And let's just say that you got 1 tail. And then the second time you flipped it, you got 1 tail. So how many heads do you have here? 0. Okay, and let's just say trial 3. Trial 3, you got 1 head when you flipped it the first time. And then you got another head when you flipped it the second time. So that means you have a total of 2 heads. And let's just say trial 4. Trial 4, let's just say that you got 1 tail, 1 head. So how many heads did you get? You got 1. And then you could just keep having many more trials, okay? But if you look, the lowest number that you can get is 0, which is why I wrote 0. And the highest number I could possibly get is 2. Why? Because the most number of times that we're flipping the coin is twice. And so the highest number that you can get for heads when you flip it twice is 2. You can't get 3 because you're not flipping it 3 times. You're only flipping it 2 times. Okay? And then another option that we can get is 1. So this would be my final answer for the sample space. Whenever you're writing sample space, you're not going to go and you're not going to do this. You're not going to write down 0, 1, 1, 2, 1, 2. Like, you're not going to write down every single trial that you get. You're just going to make like a concrete summary of what the possible options are, which is what we did here. So the sample space isn't telling you the number of times you get a particular value. It's just telling the possibilities that you can get. Okay, so it's basically just a summary. Okay, so when you see superscript C, as in A superscript C, that means complement of A. And AC contains elements not in A, but in our sample space S. Okay. So let's look at an example. So for our sample space S, the possibilities that we have is 1, 2, 3, 4, 5, 6. And let's just say that our event A equals 1, 2, and 3. So that means a complement has to include the elements that are not in A, but are in our sample space S. So in A, we had 1, 2, 3, and in A complement, we have 4, 5, 6. And that makes sense because 4, 5, 6, there's no 4 in A, there's no 5 in A, and there's no 6 in A. But 4, 5, and 6 can be found in our sample space S. Okay, and as a diagram, A complement is going to look like this. So A is a circle shown in white, and A is located in our rectangle, and the rectangle represents our sample space. And the shaded area is A complement because it's everything in our sample space that is not A. Okay, this next symbol that looks like a U is for union. And whenever you see the word union or the symbol, you're going to think or both. Okay, so A and then the symbol B, so the union symbol in B, that's going to translate to A union B. And this means an event can belong to A or B or both. So I'm going to add some color to the Venn diagram to show you what this looks like. So A union B, so it can belong to A, right? So this is A. And this part here is also part of A, so I'm coloring that in. Okay, so now I'm going to take care of the next part, which says for A union B that it can belong to B. So I'm going to color that in green. And this little section right here is also part of B, which is why I'm going to shade little parts of it in. So if we look, we have now satisfied the conditions of a union, which states that it can belong to A, which is shown in yellow, or B, which is shown in green, or both, which is designated in this region by yellow and green. And again, this little Venn diagram is in a rectangle, and the rectangle represents the sample space, which is denoted by this capital S. Okay, so now we're going to look at theorem 1.4.4 from the group. And to help us understand this theorem, I'm going to use Venn diagrams. Okay, so the first one says A union B equals B union A. Okay, so I'm just going to draw that out. Okay, so remember from the previous page that A union B includes us shading A and then B, and also the intersection, which is what I'm coloring in right now. Okay, and so A union B is the exact same thing as B union A. So like, let's just say that I started coloring this circle first and I didn't color A yet. Then I'd color this one first. I'd color this one second. And then I'd color the intersection and it would still give me the exact same answer. Okay? Okay, then A union A equals A. Okay, so here we are going to have only one circle. A. So that means it's just going to be A or both. So that's just A. Okay. Then next, it says A union A complement equals S. And remember that S is denoting our sample space. So here we have A. And so it could be A. Okay. It could be A complement. Or it could be both A and A complement, which means that our circle and the box is shaded in, which means that we're taking up the whole entire sample space, which is why, for this scenario, we equal the sample space S. Okay, and next we're looking at the union of A with the null set. So this is A. Null set is a set that has nothing in it. So that means A is in union with nothing else, which means that our answer is just A. Okay, and then lastly, we're looking at the union of A and the sample space. So that means we could be A or we could be the entire sample space, S. Okay, so notice how the whole entire rectangle and the circle are shaded in. That means the whole entire sample space is shaded in, which is why A union S is equal to our sample space S. Okay, so we can have the union of many sets. So for example, if we're dealing with finite sets, it can be A union B union C union D union E, etc. Okay? Or we can look at it as A1 union A2 union A3 union all the way to AN, with N being the number of events. Okay? And a compact way to write this is to use the union symbol, and you're going to put I equals 1, and then you write down N, because that's the total number, and you write down I for it. So then every time it'll be like, okay, I equals 1, you're going to write A1 union A2 all the way until you get to AN. Okay? For dealing with infinite sets, you can write I equals 1 to infinity AI. Okay. Okay, so when we're dealing with unions, we can also use the associative property that you probably have learned earlier for addition or subtraction. Okay? So it's basically the same idea where we can just move the location of our parentheses. Okay? So A union B union C can be written as A union B in parentheses union C, and that's equivalent to A union B union C in parentheses. Okay, this next symbol is intersection. And whenever you see intersection, you're going to think and. Okay? So right here, you're looking at A intersection B. And as I've written to the right, this translates to A intersection B. Okay? So this means an event belongs to A and it belongs to B. So let's take a look and see what that looks like. Okay? So in this Venn diagram, we have A intersecting with B, and it's located in the sample space S. Okay? So the intersection of A and B is only this region right here. Okay? It's not here, and it's not here. Why? Because this part of A, which I'm shading in yellow, is that intersecting with B? No. And is this part of B intersecting with A? No. So the only part that's the intersection is this green part. So only the green is A intersection B. So on a test or on your homework, if the teacher asks to demonstrate what the intersection of A, or if they ask you to show what's A intersection B, you'll draw your Venn diagram in your sample space. You'll indicate what's A, what's B, and you're only going to shade in this region. And then don't forget to put S on the outside. Okay. Okay, so now we're going to look at theorem 1.4.7 from DeGroot. So I'm going to draw Venn diagrams to help us understand. Okay. So here we're looking at A intersection B is equal to B intersection A. And that would just be this region, okay? Okay. And then next it's A intersection A, so it's just A by itself. And then since it's intersecting itself, that means you just shade in the circle. Okay. Then here we're looking at A intersecting with complement of A, and that's a null set because that's impossible, okay? There's never a point where A is going to be intersecting, like, just to make it clear, this A right here can never intersect with whatever's outside of it. So that's how you don't color in anything, okay? Then next we're looking at A intersecting with a null set. Okay. The null set has nothing in it. And therefore, since it doesn't intersect at all, A cannot intersect with nothing. Our answer is nothing, which is why we write the 0 with a line in it. Okay. And then lastly, A intersection S is A intersecting with the sample space. And the place where it intersects is in the circle, which is why we shade in that circle. Just like unions, we can have intersection of many events, which is what I've written below. So A1 intersects A2 all the way to AN, with N being the number of events. And we can write this in a compact manner, which is shown here, where we put I equals 1, the intersection symbol, N, and then AI, okay? And also like unions, we can also use the associative property. So again, all you have to do is you just move the parentheses and still the statements are still equivalent. So you have A intersection B intersection C, and that's going to equal A intersection B in parentheses intersection C, which is also equal to A intersection parentheses B intersection C. Okay, next we're looking at disjoint / mutually exclusive, okay? So to understand this concept, we're going to look at an example. Okay, so A and B are disjoint or mutually exclusive if they don't overlap in outcomes, okay? So for example, A is 1, 2, 3. B is 4, 5, 6. Okay, so looking at A, we look at 1 first. Do you see a 1 anywhere in set B? No, you don't. Okay, do you see a 2 anywhere in set B? No. Do you see a 3 anywhere in set B? No. So do you see how there's no overlap between A and B? Okay, so that means events A and B are mutually exclusive. Okay, so now I'm going to show you what this looks like in a Venn diagram, okay? So it's saying A intersection B and A intersection B complement are disjoint, okay? So first I'm going to show you what does A intersection B look like. A intersection B is just this section right here. Okay, next it says A intersection B complement. Okay, so first we have A. And this green section is also intersecting with B complement because this green section right here is not B. Okay? So notice how when you're looking at A, this yellow part right here doesn't intersect with the green part. They're two separate parts. Okay? Which is why we're stating that this yellow part is disjoint from this green part. Okay, so now we're going to look at De Morgan's laws. Okay, so to help us understand this, I'm going to draw Venn diagrams again. Okay, so I'm going to draw it first for the left side. So it says A union B, the complement, okay? Okay, so remember that earlier I showed us for A union B, we know that the Venn diagram for A union B is just shading in all of these circles, right? So that means A complement has to be everything on the outside, which is what I'm doing here. Okay? And for A complement intersection B complement, that's going to look like this. So A complement is out here, and so is B complement. So notice how this picture right here and this picture right here, they look the same, which is how I proved that this side is equal to this side. Okay, so now we're going to go to the next example. So we're looking at A intersection B. So remember that A intersection B is this region right here. Okay, so the complement is everything outside of it. Okay, so this is what our picture looks like on the left. And now for the right side, A complement union B complement. So A complement is anything that's not A. And B complement is anything that's not B. And it also includes this outside region as well. So if you look carefully, you can see, again, that this left side matches this right side. So again, we have shown that this equals this. Okay, so you can also use the distributive property when you're looking at unions and intersections. So I'm going to go through how, like, my thought process when I write this out, okay? So here we have A intersection. So in my head, I just kind of think like, okay, you're going to distribute it to the B, which is how we got this. And then you're going to distribute it to the C, which is how we get this. Okay? So basically in my head, I'm distributing the A and the intersection side. Okay? And then right here, where I see there's union, I just throw it in right there. Okay. Then let's look right here. So here we're dealing with A union. I just think, okay, distribute it to the B, which is how we got this. Distribute it to the C, which is how we got this. And then here I just take this symbol and then I just throw it there, and there you go. You got the distributive property. Okay, so now we're looking at A equals A intersection B union A intersection B complement. Okay? So A intersection B is this yellow portion. A intersection B complement is the blue portion. Okay? So if you look, A is made up of the blue portion and the yellow portion, which is why we can write A as the union of this yellow portion right here and this blue